In this example, we are computing the limit as x approaches infinity of x plus 1 divided by the square root of 25x squared plus x. So for this limit to infinity, we're going to use the algebraic technique where we divide by the highest power of x that occurs in the denominator. So we have in the denominator not just an x squared, but we have to recognize that it's inside of a square root. So we really have the square root of x squared, and that's what we are going to divide both the numerator and denominator by. So because we're dividing both the numerator and the denominator by the square root of x squared, it's like we're dividing by 1. So we're not actually changing the value of this limit. Now notice the numerator here does not contain a radical. So we're going to go ahead and choose to simplify the square root of x squared to be just x for the numerator. And that way, when we compute the limit as x approaches infinity, we'll be able to divide the numerator, x plus 1, divided by a nice plain x. But notice in the denominator has a square root. Therefore, we want to keep the square root when we do the division. So I'm not going to simplify the square root of x squared for the denominator. I'm going to keep it in the square root because then we'll be dividing two square roots, which allows us to do the division inside of the square root. So after you have divided the numerator and the denominator, then we are going to simplify. And I call this term by term division. So I'm recognizing that when I take x plus 1 divided by x, there's really two terms here in the numerator. So it's as if we're dividing both of those terms by x, which is going to allow us to simplify the numerator to be 1 plus 1 divided by x. And then the denominator will do the same thing inside the square root. So 25x squared divided by x squared will just be 25, and x divided by x squared will give us 1 divided by x. So at this point, we're going to show our limit laws to demonstrate how we can rewrite this limit as 4 separate limits. So we'll start with the quotient law that will let us take the limit of the numerator and denominators separately. So that'll be the limit of the numerator, but the numerator also contains addition, so I will use the sum law to rewrite the numerator as 2 separate limits that are added to one another. So the limit of 1 plus the limit of 1 divided by x. Then your denominator, you'll use the root law, which will allow us to compute the limits and then take the square root of the result. And inside that square root, we have another sum, we have addition. So we'll rewrite that as 2 separate limits being added to one another. So right now we have the limit of 1 as x approaches infinity plus the limit of 1 over x as x approaches infinity, all divided by a big square root containing the limit of 25 as x approaches infinity plus the limit of 1 over x as x approaches infinity. So we have 4 limits and we will evaluate each. So starting with the limit of 1 as x approaches infinity, that will just be 1. The limit of a constant is that constant. Then we have the familiar limit of 1 divided by x. So as the denominator becomes very large, 1 over x approaches 0. And then in the denominator, we have the square root of the limit of 25. So again, the limit of that constant will just be the constant, 25. plus another limit of 1 over x, which we previously said will be 0, as x approaches infinity. So 1 divided by this square root of 25 leaves us with a limit of 1/5 as x approaches infinity. And backtrack for just a moment, what does that actually tell us about the original function? If we look at the original function of x plus 1 divided by the square root of 25x squared plus x, if x is approaching infinity, that means we're moving along the right side of our graph, looking at the right end behavior. And the value of our limit, which is 1/5, is basically telling us that we have a horizontal asymptote of y equals 1/5. And that's on the right-hand side of our graph. It's the right end behavior. Now we want to compute the limit as x approaches negative infinity of the same function. So we'll use the same strategy where we divide both the numerator and the denominator by the highest power of x that occurs in the denominator, which will still be the square root of x squared. And we will still recognize that the numerator here, x plus 1, it does not contain a radical, so we do want to simplify the square root of x squared. But we have to consider the difference now that x is approaching negative infinity. So previously, on the last example, when we simplified the square root of x squared, we said that that was equal to x. But that's technically only true if x is a positive number, if x is greater than 0. Because notice, let's just say if x were equal to -3, if that were the case and we had -3 squared, and we were taking the square root of -3 squared, it would be wrong to say that our answer was -3. That is not a true statement. The correct answer is +3. So we have to be very careful when x is a negative number. So the square root of x squared will be equal to the opposite of the x value if x is a negative number, if x is less than 0. So on this problem, when we simplify the square root of x squared, we're going to end up with the opposite of x because x is approaching negative infinity, therefore x will be a negative number. So we'll be utilizing this second case here as we simplify. Now in the denominator, we're going to leave the square root of x squared because the denominator contains a square root. So we want those to be similar. We won't simplify. So let's do our division. We're taking x plus 1 and dividing that by -x in this case. And then the square roots are being divided, which allows us to do the division inside the square root. And next we're going to do our term-by-term division. So dividing x plus 1 by -x is the same as x divided by -x plus 1 divided by -x. So the numerator of our limit will be -1 minus 1 divided by x. And the denominator will still be the square root. 25x squared divided by x squared is 25, plus x divided by x squared will give us +1/x. So now we're to the point where we want to use limit laws to rewrite this complicated limit into 4 simpler limits. So we'll use that quotient law, and then we will also use the difference law. So the numerator here contains a difference, -1 minus 1/x. So this will be the limit of -1 minus the limit of 1/x as x approaches negative infinity. And the denominator will use the root law, which allows us to compute the limits inside of the square root and compute the square root at the end. So we'll have the square root of the limit as x approaches negative infinity of 25 plus the limit as x approaches negative infinity of 1 divided by x. So we now have 4 limits to compute. So the limit of negative 1 as x approaches negative infinity is still negative 1. Then we have the limit of 1 over x as x approaches negative infinity. So as the denominator becomes more and more negative, we end up with a value very close to 0. So that limit will equal 0. All divided by the square root of the limit of 25 as x approaches negative infinity, which is just 25, plus the limit of 1 over x again, which is 0. So this time we end up with negative 1 divided by the square root of 25, which leaves us with a final answer of negative 1/5. So this means that we have another horizontal asymptote of y equals negative 1/5, and that asymptote pertains to the left side of the graph because we were computing the limit as x approaches negative infinity. So we basically have found the left behavior of this graph. The left behavior of the graph is that it will level off along the horizontal asymptote y equals negative 1/5.